Hey guys, welcome back to my YouTube channel. So today we are going to continue our discussion on the combination circuit. So today our circuit that we are going to build and design is comparator. So let's take a 1-bit comparator. So comparator is nothing but comparing 2-bit. So whether A is greater or B is greater. So like that only we are going to compare. So let me draw a truth table. So this is 1-bit comparator. So we are going to compare A and B. So possible input is 0, 0, 0, 1, 1, 0, 1, 1. Okay, here three kind of outputs is possible. So whether A is greater than this X is implying the bit A is greater than B. So Y is imply that A is less than B, and Z will imply that A which is equal to B, right? So here the both the bits are equal, so this should be need to set to 1 and these are 0. Here B is greater than, so this is set to 1 and remaining 0. So here A is greater than, so remaining are set to 0. Here both are equal, so 0, 0, 1. Okay, so X can be written as X has only one input. If we write in a min term, then that is A bar B. So Y also have one term, that is A B bar. Z has two things. We can clearly see that is a function of XNOR. So I am directly writing as XNOR. Okay, so we got the three inputs. So from here we can directly build a circuit and do it. So I am leaving this to you. So I am going to say how we can. This is 1-bit comparator. So how we can compare for 2-bit? So I will just give you a clue. So you guys can do K-map and do it. I am leaving this to you. So I am just implying how we can do it. So what are the conditions? So A means we will be getting not like the previously there is only 1 bit, but here there is A0, A1, A0. So B means that is B1, B0, right? So there is three conditions that we need to follow. So if A is greater than B, what are the conditions that we can say? If A1 is itself is greater than B1, then we can clearly say the condition is accepted. So if A1 is greater than B1, then that condition says that A is greater than B. Or this is one condition. Or if A1 which is equal to B1, the first bit is 0 and second bit A0 is greater than B0, then also we can say the A number is greater, right? So this is the first condition. So this can be written as, so this logic is x1 R means plus, equal to means that is z1 and x0. Okay, so I am getting this from previous thing. So we have stated x is means A is greater than, if equal to means we calculate as z. So that only I have done here. Okay, so I hope this is understood. So let's take a condition that B is greater than A, right? So B is greater than A, the same reverse logic, A1 is less than B1 or A1 equal to B1 and A0 which is less than B0, right? So this can be written as y1 plus z1 y0, right? So if A is equal to B, there is two possibilities, that whenever A1 by B1 equal to, and because both the bit need to be equal, so A0 B0. So this is written as z1 z2. So now let's see how we can write a thing for this. So we know that xi which is equal to ai bi bar, yi which is equal to ai bar plus bi bar, bi normal bi. So zi which is equal to ai XNOR bi, right? So let us build a truth table. So how we can write this one? So I am writing a truth table here itself so that we can compare it easily. So here 4-bit we have to take into account, right? So 4-bit I am using here. So which is A1 A0 B1 B0. So thing is that y z y x z x y z. So 0 0 0 0 0 0 0 1 0 0 1 0. So like that way we need to write. So I am leaving this to you. So you guys do. I am writing last 2-3 bits. So 1 1 0 0, then 1 1 1 1. So I'm just taking some random things. Okay, so let's do. So 0 0. So all thing is same. So which is 0 0 and z is set to 1. So here b0 is greater than 1. So we know y is greater than, and these are set to 0. So here b1 is greater than 0. So here this is 0 0. So this is dot dot dot. Here if you see the b number is 3, but a number is just 2. So here also b is greater than, so which is 1 0 0, and here a is greater than, so a 0 0. So here both are equal, so 0, 0, 1. Okay. So here we need to find the functional, the summation m. So at what are the values at which these things is 1. So I'm writing at what are the values it will be 1. So you guys do a k map and do it. So this will, what are the values it will be 1 is the 4 comma 8 comma 9 comma 12 comma 13 comma 14. So these are the values at which x will be 1. So summation the y at whatever value y will be 1 is that 1 comma 2 comma 3 comma 6 comma 7 comma 11. And what are the value that z will be 1 is that summation m is equal to 0 comma 5 comma 10 comma 15. Okay, so I'm leaving this to you. So you guys just draw the k map for these three function and suggest a function there. So if you guys find out, please post in the comment section. Then we can similarly like last thing we have directly drawn the circuit here. So now we need to use the k map. So use k map and find the answer. So use k map and find x, y, b. Okay, so I hope you guys able to understand the things, right? So even if you guys not think, so this is the logic. So this is how the function will look like. So if we draw here, so x1, we know the x1 function will be a1 b1 bar plus z1 which is equal to a1 x0 b1, which will be product of x0 which is equal to a0 b0 bar. Now we have to expand this and then multiply inside, so this will take more time, but if you use k map we will be directly landing into our final equation. So I am leaving this to you. So 2-bit comparator, please try as a homework, so please do it. So now we can skip into next topic. So that is very important topic in our discussion, that is multiplexer. Okay, so multiplexer. So multiplexer is a device which is a combination circuit only, which contains many input but only one output. Contains many input but only one output. Okay, so this is what the thing. So how this will work is the based on the selection line it will work. So let me draw one diagram so that you guys can able to understand. This is how multiplexer will look like. So if there is two selection lines, so selection line is a concept. So based on the selection line only our output will be determined. So only one output will be there. So for two selection lines there will be input. Based on the input only selection lines will be. So if there is 4 input there will be 2 selection line. This is 2 part 2, right? So that's why. So which is called selection lines will be called as S0, S1, and the inputs will be called as I0, I1, I2, I3, and output is 1. So this is called as MUX. So this is we call as MUX. So this is how MUX will look like. So this is 4:1 MUX, right? So based upon the selection line, output will be selected. So let me start like with this. So let me draw a truth table for this one. So based on selection line, it will be, output will be taken. So MSB at outer level. So this is so y. So 0 0 0 1 1 0 1 1, right? So if 0 0 is taken, I1 will be output. So y will be I0. Sorry, I0 I1 I2 and I3, right? So the inputs will be switched based upon the selection lines. So let's see how we can represent the output. So from this truth table we can clearly note the output can be represented as, so just a representation of these things like S1 bar, S0 bar, then the output will be I0 plus S0 S1 bar plus S0 I1 plus S1 S0 bar I2 plus S0, so S1 S0 I3, right? So this is how the circuit, this is how the logical function output will be looks like. Okay, so let's see, we have already see universal gates, right? So whether MUX can act as a universal gate, so it's an interesting question. So we know that universal gate is a something with the help of that gate we can do any kind of functions. So let's see whether MUX can be used to do all these operations. So first let's try to implement AND gate here. Okay, so we know the output of AND gate, that is AB. So for the single input, if there is a one bit MUX, so there isn't one bit MUX, there is only one selection line, then output will be resembling on S0 bar I0 plus S1 I1. So this we know. So we need to compare, we need to make both the things same. So we are using 2:1 MUX. So 2:1 MUX means there will be only one selection line and two input and only one output. Okay, so let's make this possible. So let's take AND gate here. So this is AND gate. So we have to fix any one of the input. So let's take B as a input and A as a selection line. So let's make A is equal to 0 here, and take another one AND gate with the same thing. B is an input and A which is equal to 1. So in this case what will happen? Our output will be 0. So in this case what will happen? Output will be B. So this is what we are chasing. So we are considering this as I0 and we are considering this as I1. So how we can build the circuit is that, so if you guys are not understand, please wait until I completing this diagram. So after that you can clearly understand it. So this is 2:1 MUX. So this is the selection line S which is equal to A. Output is Y, right? So here we need to choose this output. So first one is 0 and second one is B. So now let's write it. So A bar 0, A bar 0, that is 0. Then this AB. So 0 and anything is 0. So our output is AB. So here you see we have achieved the AND gate. So we are able to achieve AND gate with the help of this. So let me do another one thing. So let me try another one of the gate so that you guys can also able to do it. So let me try NAND gate or OR gate so that you guys can able to understand it. So let me try OR gate. So let me take OR gate. So using 2:1 MUX. Okay. So OR gate output Y which is equal to A plus B. So simple thing. Let's take two OR gate. So we are fixing B as the input and we are giving A is equal to 0. We are fixing one input and giving, we are fixing one and we are giving 1. So here output will be 1, here output will be B. So let's take a MUX. So this is 2:1 MUX. There is one selection line which is A. Now here the output is equal to B and here the output is equal to 1. So if we choose it, then this is equal to Y. So Y can be written as A bar B plus A, right? So this is what the logic that is coming here. So this is how this will look. So A bar B plus A into 1. So if we use to convert this into canonical form, like if we convert, let's say we convert it to canonical form, AB plus A, B plus B bar. So if we expand it, A bar B plus AB plus A B bar. Okay. So here we can take something common. So here let me compare this one. So let's take B common. So if we take B common, then it will be A plus A bar plus A B bar. Okay, so this will be 1. So B plus A B bar. So here if you see, we are facing some difficulty to reduce it. So I'm suggesting you guys to go with the K-map. So use the K-map and reduce it. So I'm sure that this will looks as it is, like previously how we get this input. So AB we get, right? So similar to that, here also we can able to get. So here B plus 1 is equal to 1, B plus 0 which is equal to B. So we are doing correct. So this here is a B and here it is 1. So A bar B plus A B. Okay. So this will looks like B. So if you guys are confused, then let's take a truth table and let's compare the output. I already said the same logic can be done in different ways. So let's take A bar B plus A. Okay. So 0 0 0 1 1 0 1 1. So if we apply 0 all the things here, so A bar B is equal to here it is 0, here it is also 0. So this will be 0. So here if we substitute a bar b, so this is b1 plus 0, so the answer will be 1, so here will be 1. So if we substitute this one, so a is 1, so it will be clearly 1. So here also a is 1, then clearly 1. So here we can clearly see this is a function of OR gate. So this is truly same like OR gate. So if you guys need to reduce this into OR gate, please use a k-map to try. So if you do that, then we can definitely able to get this function, but it needs some analytical skills and understanding to do that. So I have proved that whether this logic is same as OR gate with the help of truth table. So you guys can also please make a note of it. So similar to this, we can do whatever the gate like NOR, NAND, XOR, any kind of gate we can do, because MUX is a universal gate. We can act this as a universal gate. So I'm leaving this to you, so you guys can try what are the things that you guys needed. So we are going to shift to next topic. So to implement any two input gate or a two variable function using a 4:2 MUX, we just need to use the k-map. So we can directly map a k-map into that stuff. So let's see some kind of things like that. So let me give you one example so that you guys can understand. So logic function implementation using MUX. So here I am giving you a question so that you guys can able to understand it. So here we are selecting selection line S1, S0. Here we are giving two input, that is A, B. So here in the question itself they are given four inputs. So which is equal to C, 1, 0 and C bar. So this is 4:1 MUX. The output is F. So they are asking us to find what will be the output. So I'm leaving this to you. So please find this using any kind of method you try it. So in the next class I will be posting this answer. So homework. So I'm leaving this to homework. So if you guys able to solve it, you guys can clearly you can solve all the questions in the digital electronic combination circuit. So I'm suggesting you guys to just to copy the thing in the truth table. So I'm giving one more clue also. So please use truth table or k-map table in order to fill this one. So this is simple. So I'm giving this clue. So as it is a 3-bit, right? So A, B, C. So 3-bit is there. So I'm leaving this to you. So use any kind of k maps like this one. So use this one. So you guys can use it like this one. So please separate the things. So like this way mentioned, even vertical or horizontal, any kind is convenient. You guys can use it. So I'm leaving the clue to use like this. So if you use it like A, B, C. So as C is the selection line, AB is the input selection line. So I am making significantly like this way. So in order to make you guys to understand. So this is 0, 0. So just mimic the thing. So must mimic the each thing. So if 0, 0 is coming, what will be the output? So output will be C. So what is C? So we have to put 1 here. So like this way, you just complete all the thing and then try to answer it so that you guys can able to understand. So I'm leaving this to you. In the next class, I will solve this answer. So please post the answer in the comment section. Like post the function. What will be the function logic that you are getting? So like, share and subscribe channel. Stay tuned for next lectures.